Thanks very much. I'd like to start by thanking the organizers. It's a pleasure and honor to be in a network symposium. I would like to talk to you about non-reciprocal interactions and a particular way that you can use them to build molecular or colloidal structures that will change shape in a way that will be specified. A number of people have worked with me on non-reciprocal interactions over the years, and also senior collaborators, but in particular today I want to talk about the work of Saeed Osat, a postdoc in the group, and Jacob Metzen, who graciously you guys sent over from Cambridge, so I'm very happy to have him as a graduate student. So essentially, this is the idea. So it's the molecular or colloidal equivalent of dancing like Mick Jagger. Basically, you want some building blocks that you will engineer, and you don't throw them in the solution and provide the fuel that is needed. They will find each other, form a structure one, and then they will have a program basically going through several cycles of changing different structures. This could be conformation of the same thing, or it could be other structures, and this could be basically forming different functionalities. It could happen by disassembling and reassembling completely fresh every time, or it could be just changing the shape of the same thing. And essentially, the idea is how to learn the rules of the game, namely the physics, so that we can achieve something like that. So one example could be thinking about something like a sperm. So what is a sperm? It's basically a self-organized protein structure that happens to have access to energy and a mechanical bifurcation that will create a traveling wave along its tail, which breaks time reversal symmetry and interacts in the right way with the hydrodynamic, with the fluid environment around it, such that it can move in a directed way, so swim, and then it also has this chemosensing machinery and a cargo of DNA that it will deliver. And this is basically the sort of thing that one would like to be able to engineer or build. Here's a Brownian dynamic simulation of a system that I will describe. Essentially, you will see that these colloidal particles that have non-equilibrium catalytic activity will undergo random motion, and then at some point they will form the right structure with the right symmetry breaking in terms of access and the right bifurcation and the right interaction with the environment, so that they can propel themselves. So how can we do things like that? One thing which I would like to emphasize here is that for this kind of program, at least for the way I look at it, the real physics is very important. So I don't want to just write an Ising model and say that there is some specific rule, because I always have in mind that I should be able to talk to an experimental colleague and together with the colleague, find a way to build something that actually works in the lab. So just having some abstract imaginary model with some rules, agent-based type rules, will not make it for this particular agenda. So let's think about the right physics. The right physics will come from interfacial transport mechanisms. These are force-free mechanisms in which gradient of thermodynamic potentials like thermal energy, electrostatic energy, chemical potential, and so on will lead to relative motion of fluid and colloidal particles, either vesicles through osmosis or solid colloids and movement through diffuse euphoresis and so on. These are actually quite subtle mechanisms, so despite the fact that they have been around for a very long time, people keep rediscovering exactly what they are and what they mean and how one should think about them. But bottom line is that they are everywhere and they work pretty well, and we can think about them as essentially non-equilibrium processes for these particles that will be specified by two quantities or two, let's say, material parameters. One is the so-called activity. So in this case, I'm using the language of diffuse geophoresis, so gradients in chemical potential or concentration driving the motion of colloidal particles relative to the solvent or fluid. So the chemical activity describes the flux of the extra particles that you release in the system or you consume, and so on. And this is essentially a measure of the non-equilibrium activity or deviation from equilibrium, and it can be positive or negative. I call it alpha. And then there is mobility, which is essentially an Ansauger coefficient, and you can calculate it for different specific transport mechanisms, for thermophoresis, diffuse phoresis, and so on. And this is actually a full-time job. If you want to calculate this quantity, you need to bring in the nonlinearities, and you can introduce all kinds of interesting features. And also this can be positive or negative. Soon we will see that these two parameters will basically specify everything, at least in the far-field limit, where the problem has a simple mapping to a Coulomb system. So what you're dealing with, let's say you want to study how two particles that are different interact with each other, and they're both catalytically active, so they both release particles essentially as if they have these sources. So let's say alpha 1 for this one and alpha 2 for that one. And then they produce in stationary state concentration fields that are solution to Poisson equation or diffusion equation, decaying as 1 over r in 3D and being proportional to this rate of activity alpha. And then the other particle will respond to this with its mobility, essentially gradient of that potential, almost like a potential, will determine the velocity. So particle number 1 will have a velocity which is essentially gradient of 1 over r and proportional to alpha 2 times mu1. And particle number 2 will have the same thing, proportional to alpha 1 times mu2. So here we have a generalized Coulomb or classical gravitational description in which we have two types of charges or masses. The one that produces the field is different from the one that responds to the field. And by being different, basically you break the action-reaction symmetry, because essentially unless you tune alpha 1 times mu2 to be exactly equal to alpha 2 times mu1, generically you are always in a situation where these two will have this kind of symmetry breaking. And this will have very, very serious consequences. And if you think about it, this already brings in character to the world of these colloids. So it makes their interaction like relationships. So it's not guaranteed that, you know, two people always like each other exactly the same way. And here we have the same feature for colloids as well, right? So this is a situation which is designed to give you an interesting behavior. So one of the colloids doesn't care about the other one, but the other one is madly in love. And what happens is that you form these complexes that are self-propelled spontaneously. Essentially, the particles, when they form these bound states, which are stabilized by the excluded volume interaction, which is an equilibrium interaction, will adopt a very specific shape. So the AB molecule will have this polar shape, linear shape, and the AB2 molecule will have a 60-degree angle between the two bonds. And this is a self-organized structure, so they can exchange monomers and also coexist with free monomers. You can tabulate the kind of structures that you can have. So these are literally structures that will form spontaneously with the specific shape, so not just wobbling around, but having specific angles that they choose, and based on their symmetry, they will essentially exhibit some kind of function. So these are all axially symmetric in 2D, which means that they exhibit self-propulsion, translational propulsion as their function or activity. These basically spin at, let's say, a relatively noticeable velocities, and these are too symmetric to essentially show any kind of mechanical activity. So you're beginning to have a flavor of an opportunity or a possibility to design surface properties of these catalytic colloids such that they will find each other in solution, form complexes of a specific shape, and the shape determines the specific function. So exactly like in proteins, you will sequence it, and it will fold into a three-dimensional unique shape that will achieve a very specific function because of that shape. So this is essentially very similar. Now, the shape doesn't have to be static. You can have situations where you achieve multiple shapes, and then you can have barrier crossing transitions between them. And this is AB3 is one case. You can have the T isomer and the Y isomer and an activated fluctuation between them. So here you have an emergent run and tumble behavior. So a system with an emergent discrete set of configurations coming out of a system that has basically access to all possible conformations in principle. So it's a reduction of the symmetry of the system. This one basically breaks time reversal symmetry for the propelled one only in the form of polarity, but in fact the sperm that I showed you earlier is an example of the same structure, and that one breaks the time reversal symmetry also in the form of the sequence of conformational changes that it undergoes. And you can make also other structures that are bigger, etc. So this is not just a theoretician's dream. In fact, people have started building these functionalized mixtures, and they do find each other and make self-propelled molecules, and also other sort of more complicated structures have also been coming out recently. So far, I talked about only sterically symmetric sort of catalytic activity. So the simplest way that you can drive the system away from equilibrium, of course, you can make polar particles out of them, and so Janus particles. And then when you build essentially the orientational interaction and the positional interaction, you can create all kinds of different behavior. In particular, you can create frustrations that will lead to formations of different types of bound states or scattering type behavior, simply because you can independently frustrate, let's say, the degrees of freedom. So the two colloids could have, for example, positional attractive interaction towards each other, but they might want to align away from each other and swim away from each other while being attracted from the positional point of view. So you can frustrate all the degrees of freedom and create different kinds of behaviors, and people have been looking at the sort of phase behavior that you can have out of these systems also. So more specifically about the model that I want to study. So I want to switch to much more complex structures and talk about self-assembly. So we heard already today about the notion of self-assembly, and in particular, I think these papers from Zorana and Michael Brenner and Arvin Morgan and Stan Leibler have been shown. So essentially, the idea is that it will be desirable to be able to have a number of building blocks that we design such that they will have such interactions that they can find each other in the solution and form different types of structures. And then it will be very interesting to find a way to, first of all, trigger, let's say, formation of a specific structure. So that's called seeding here. You will create a small seed of one of the structures, and then it will naturally grow into that particular structure. And then also later we will discuss the possibility to make transitions between them. As was also mentioned earlier, you need to have specific interactions. So by just having non-specific interactions, you will basically make very quickly complicated structures that are essentially not very easy to, let's say, be selective about. So we want to use the same kind of concept, and everyone knows in the field of self-assembly that as soon as you start having dreams like that, you run into trouble with the so-called chimera structures, because basically you're dealing with a system with many, many degrees of freedom, completely locally initiated or activated to form, or seeded to form different structures. And of course, as soon as you have more than one structure, there's every possibility that things will happen going in different directions, and then you will form things more often than not, that look like a beast. So having a hand which belongs to one structure, and a tail which belongs to another structure, and a head which belongs to another structure, and then you get stuck. So that's it. And this is a massive challenge in this kind of multifarious self-assembly, because you want to ideally be able to have control over this. Okay, so once again, this is the plan of action. We want to find a way to start from a pool of tiles, here trivialized to a model, but I wanted to qualify that I'm not the sort of theorist who only talks about lattice models and so on. I care about the implementation as well. But for the sake of the rest of the discussion, let's think of this level of abstraction, and then imagine that with these 16 tiles, we can make a number of structures. Essentially, every unique structure is defined by the exact position of the specific tiles and the exact ordering that you have of these 16 ones. And then you want to find a way to engineer these transitions between them as time goes on. So how does that work? First, we need to find a way to make structures that can be memorized. So this is basically a memory engineering task. And then you want to have a system in which you can retrieve them, essentially using the seeding procedure that I mentioned. And then you want to engineer the transitions between them. So as others have done, so the works of people like Zorana and many others, you basically need to engineer the equilibrium interaction between these building blocks. And for them to be specific, you need to make them directional. So that's the typically challenging part of the interaction from an experimental point of view. There are now many colloidal systems that have directional interactions. For example, the famous lock and key mechanism, and there are many that use DNA conjugation, but there are also others that use other types of patchy interaction and so on. So what you want is to have, and I apologize for tilting everything 45 degrees. This is the only way that you can type these interactions and still get away with having exact prescription of what you mean by that. Because if you were to use horizontal and vertical, we would actually not be able to do that. So what you have here, I'll just take you step by step so that everything is clear. So A and B can attach using this phase. That will be basically interaction UB / A, and then they can attach this way. So just exchanging the position of A and B, and that's another interaction. And then you can have it also on the sides. So A being on the left of B, and then A being on the right of B. So A being below B and A being above B. 4 different directional interactions in 2D. And then we also need to introduce these so-called non-reciprocal interactions, and we have 8 of those. So A can attach to B from the left, B can attach to A from the right. These will form the same equilibrium structure, but the non-reciprocal aspect of them will be different. And then B can attach to A from the left, or A can attach to B from the right. What do I mean by this? You can see it, and also these 4 other partners. You can see it in this example. So if you remember with my catalytic colloids, I told you that what A feels from B is different from what B feels from A, in the same interaction. That's exactly like relationships, and it works in the mechanics also. So here, when you want a B particle to come and join this existing cluster where A is a part of, essentially what matters for the rate of this transition, or for the non-equilibrium dynamics of this particular bond to form, is what B feels in this interaction from A, right? So that's basically this one. But when the opposite happens, so B is an existing member of this cluster, and A wants to join it from the left, essentially forming the same equilibrium structure, then what matters is what A feels in this interaction, right? And that's basically this rate. So
are you sort of saying that it's just you have different interactions conditional on whether they're already in tensor or
Well, this is how they show themselves in this question of self-assembly. But in general, if these two were also in the free bulk, what would happen is that they would form a bound state exactly with the same shape, but then they will be self-propelled because, you know, in the end there is this, you know, the velocities have an average which is non-zero, and they will move in some direction. Now, actually, in what I'm going to show you, we only focus on the structure formation. So we basically suppress the self-propulsion. But in version 2.0, we will have the self-propulsion also to actually see whether that helps with the speeding up of the process and so on.
Because your self-propulsion will be based on your A and B will be the different species included in your animal, right? They'll be distinct entities.
Yes, so think of them as two enzymes that have different catalytic rates.
Okay.
And then, you know, and also being part of formation of the complex. Okay, so this is the model as will be implemented. And here is one example of how you can make a transition. So this is a transition, is not a stochastic search in the complex landscape. It's a directed transition, and it happens by very specific steps. So I hope you can read colors. Actually, I struggle myself with colors. But you know, if you can read the colors, then all the information should be here. So first, I want to highlight that these are two different structures, and every single step that we go through this cycle, there is a red line, which is basically showing the location of the interface between structure number 1 and structure number 2. I hope you can see that. So for example, here, it's only one monomer that is left. So the red line, which is the interface between the structure, which is the structure 2, the new structure, and this is the remnant of the old structure. Here is this one. Here you can see it's basically this line and so on. So that's what you should look at. Now the transition from this structure to that structure is triggered when this tile finds the blue tile, so this light green tile, although there are so many colors that it's not very useful to name them, but you can sort of see the contrast, at least for the blue part. What is important is that this coming light green tile is engineered to have 3 non-reciprocal interactions. So this is the one that is the first invader, so it has to have these basically non-reciprocal interactions with the 3 neighbors that it will create, such that it can kick out the old one and create the new bound state, which is basically this structure here. So you can see that the green has achieved now 3 new links and essentially eliminated 3 old links. So that would be the price to pay for that. Then the next particle to come is this one. As you can see, this one has to have a non-reciprocal interaction with this tile, but not with the one that just joined, because that one is a member of the same self-assembly structure, and they are essentially memorized just through the equilibrium interaction. So this bond is a solid line, and this bond is an arrow. And you can basically go through the cycle and convince yourself that all these transitions are going to happen, essentially shifting the red line, the interface between the old and the new. And you know, during all these intermediate steps, you basically you're dealing with chimeras, but these chimeras have moving boundaries. And I will come back to this concept later because it's a fascinating sub-story.
What sets the order in which the events happen?
Well, what sets the order is that stochastically you try everything because you have access to a bath of all these tiles, and they keep coming and essentially trying their luck. And the one that has been chosen to have the possibility with the rates to basically replace that one will succeed, and then this will be accepted. So
does that mean that those are the only possibilities once, say, the blue one has been injected and the green one has?
In this implementation, yes. So we basically focus on compact structures that are made of all of the tiles, and the individual tiles are engineered so that they have these specific rates. But we can think about things like capacity and yield and so on. So these are all things that I will come back to later. Okay. So then if you essentially do the simulation, I will not talk about the details of the method. You will find a phase diagram or a state diagram for the different states that you can have. It's not always going to be basically a success story, and you can get all kinds of different states. You can get basically this state of multifarious assembly. So from this point onwards, I will stop keeping essentially the individual tiles or the identity of the individual tiles or the colors, and instead I will just block color every given overall state or structure. So here I have black. That means one specific sequence of all the blocks that I have in the system, and these are much bigger blocks than 9 or 3 by 3 and 4 by 4. Essentially, when you see a solid color like this one, essentially invading another solid color, that's this interface that I told you about. Essentially, one structure invading the other structure, so that you get this shape-shifting property. So you get equilibrium multifarious assembly, having different structures that you can retrieve. You get the chimeras, you get the so-called liquid because of the dense clusters, you get the so-called dispersion because of the dilute configuration, and this shapeshifter. And here you can see time evolution of this quantity that is called an overlap, basically taking whatever structure that you have and calculating the overlap of that with the existing structure. So here, for the case of 4 possible structures, and you can see that the overlap in the shape-shifting state will switch exactly basically between 0 and 1 and go through a very specific sequence, which is the one that is designed. And here you can see entry production in dashed line, essentially highlighting which part of the process is most non-equilibrium. So here's the phase diagram, which is quite well known. In fact, I think it's maybe from the first from the group of Michael Brenner and Stan Leibler that worked on this. Basically, the 2 parameters that we have for the equilibrium description is the chemical potential of the tiles. So that's the density of the tiles, and this binding energy, which we choose to scale with epsilon. So what that means is essentially all the bonds are defined by assigning the same energy scale epsilon, and then basically you have zeros and ones depending on whether they exist or not. And later on we will have the same feature with the non-reciprocal bond. So all of up here you will have chimera structures, and basically down here you will have dispersion and the liquid states, and it's this blue triangular shape that will give you at equilibrium access to the multifarious self-assembly structure, which means in this region you can create different structures and expect them to be retrievable when you seed them, essentially in this case for 4 different structures. And these are different measures that we chose to check that we have the phase diagram boundary, the state diagram boundaries correctly. As you switch on this non-reciprocal interaction, which is controlled by this parameter lambda, so essentially every non-reciprocal interaction will have a strength lambda when it's non-zero and 0 when it's 0. Then you start having, so the phase diagram itself or the state diagram will change its boundary, and it will accommodate this region, which is shown by this red dashed line, and that's where basically the shape-shifting happens. So it is a part of the multifarious self-assembly regime, which now allows for the shape-shifting sequence to happen, and this is essentially larger and larger as lambda is cranked up. There's always going to be a minimum and a maximum lambda. There are two mechanisms. So lambda minimum basically is the minimum value of the non-reciprocal interaction that you need for the shapeshifting to start. And maximum is basically when it's too much. And I don't want to, I will not talk about the details of what they are, but we understand them well. And basically they come from competition between different mechanisms. So we can look at different features. For example, here you can see regions in lambda between the minimum and the maximum where the shift happens, and this quantity f essentially measures the fraction of the time where in the simulation run we observe this very robust sequence shapeshifting. We can identify two different time scales. So one is the time scale that you set everything up, let's say randomly, and then you form the first structure by having essentially diffusion and trial and error. And that's essentially not different from what you have in equilibrium self-assembly. And then once the structure has formed, you have another time scale which is controlling the shift. And you can see here that that shift time scale is a lot smaller than the formation time scale, but it has the same scaling with the system size. And you can also look at yield. In fact, sometimes when the strength of non-reciprocity is too strong, the structures start to switch before even they have formed, so they are prematurely moving. Then you can look at capacity. So this is a similar thing to the concept of notion of capacity in spin glass type models. And so this M here is the number of states that you can store in this memory as a function of the non-reciprocity parameter, and the sweet spot or the region of interest is basically down here. So you need to have a specific region for the non-reciprocal interaction to be able to have this type of behavior as a robust pattern. It's possible to basically understand this shape-shifting as a cycle in the space of conformation. So if you use these overlap parameters, let's say in a case where you have three structures, essentially the trajectories that you would have when you have this non-reciprocity will be a cyclic trajectory around that. And this is contrasted from when you don't have the non-reciprocity, and essentially every structure has its own basin of attraction and a very visible barrier in between them, which are the kinetic barriers that I talked about. And I come back to this point a bit later, and we also looked at Brownian dynamics version of that. Okay, so
basically your question time.
Okay, so just very quickly, if I may, basically I told you about these kinetic traps for chimeras, and one of the things that would be very interesting to do is to engineer a system that can do what an enzyme does, namely lowering the barrier when the time is when it's needed in a non-equilibrium way. We thought that this non-reciprocal interaction would be a good system to try that out. Essentially, you can prepare the system with having different fractions of the two states that can make a chimera state, both of which happy equilibrium states, and then ask the question, what happens when you introduce the non-reciprocity? And it turns out that yes, you can cross the barrier if the system is in a cycle with many states. You will do it by using defects, and I'll come back to that. But first, when it's just a transition between two states, it turns out that what happens is that you start forming this front of one invading the other, and the front basically shows Kardar-Parisi-Zhang universality behavior, and even the fluctuations of this height profile show Tracy-Widom distribution, which is really cool when you are making a transition between two different states. Here you can see the video of this growing front from one structure to the other one, but I guess you can get the idea. And then the defects also basically enter when you seed the system or you expect the transition between parts that are not neighbors. So if you have a mixture, let's say here, of S1 and S3, if you just have S1 and S2, you have to wait until S2 is nucleated, and that's a normal kinetic barrier. If you have S1 and S3, you have to wait until S2 is nucleated, and then that will create, or seed it yourself, that will create these defects, which basically have the right ingredient for the cyclic behavior, and that can anneal the system very, very quickly. So I will skip on this and come to the conclusion. So basically the idea is that I think using non-reciprocal interactions, which are very real and very possible to implement in molecular and colloidal non-equilibrium soft matter, you can do a lot by using very, very minimal ingredients, and even have the potential to create shape-shifting materials and things like enzymes or artificial barrier crossing, active barrier crossing facilitators. And with that, I thank you for your attention and leave you with this teaser for another work which I didn't talk about. So thank you.
So the example of the non-reciprocal interactions you showed was that essentially a concentration field set up outside one particle with the other particle interaction. Mm-hmm. So when a particle moves, there's a time scale to readjust that concentration field.
Correct.
So how does that affect the kinetics?
Well,
it will affect it, and it will modify the interaction. In some
way. It depends on the numbers. So you're dealing with diffusion coefficients of chemicals. I don't know, like hydrogen peroxide. So this is a very large number. When you think about colloidal scale, let's say, moving. But if you're dealing with an enzyme, which is a nanometer compared to, let's say, hydrogen peroxide, which is an angstrom scale, then of course this becomes more important. You have only 1 decade of separation between their time scale.
The interaction also depends on how many. I mean, the 1 over R is an infinite system with no other particles. So if you're
So I mean, if you're asking about the long-range nature, you can screen the interaction and still have the same effect. In fact, the field theory that we wrote as the non-reciprocal Cahn-Hilliard model is for the screened version, and that is much more general. I just use this for simplicity.
Question about this mechanism. So the non-reciprocity depends on the product of property of particle A and particle B. So you've got n species of particles, you've only got 2 n possibilities there, but n times n minus 1 pairs. So there must be a lot of constraints on the possibilities of the pairwise interaction.
So that's a very good point. This particular implementation will allow essentially for these pairs to determine the strength of the interaction. So you choose one alpha and one mu. I guess if you need more, you can think about other things to implement. And I didn't talk about specifics of starting to engineer different things, but you could think about that if it is needed. So in general, I mean, just doing simulation, because we haven't done the full enumeration for the large scale system. As soon as you bring in, let's say, I don't know, 4, 5, 6, 7 types of these things interacting in a non-reciprocal way, they start showing so many weird types of regimes and so on that we haven't started thinking about their shortcomings yet. But of course, there are combinatorial constraints, as you mentioned. I mean, here you can see chiral symmetry breaking, actually. So for Stefan, we talked about it yesterday.
Any other questions? Not, let's thank Ramin and others.